Okay, here we go. We're shooting. Today we're going to talk about Honda. God, did I spell Honda wrong? It's H-O-N-D-E. Okay, it's supposed to be H-O-N-D-A. I don't know what got into me. Honda Electronic Blower Motor Control. Basically, this is not an automatic climate control system. It is a manual system, but yet the blower speed is controlled by what we call a blower power transistor, which is communicating with the HVAC module. They call it the audio HVAC display. And as you can see there where it says blower speed, that is the driver controlled blower speed control, which moves between low and high, actually between on, low, and high. And that is part of the HVAC display. And then the signal is an analog signal sent over to the base of a transistor in the blower power transistor. You'll see that on the scope. I thought it was duty cycle. It is not. It is a sort of a potentiometer-like analog voltage, much like a throttle position sensor. There is the blower relay. It has got 40 amp fuse protecting it. It is ignition fed through the relay coil and a hard ground at the blower relay. It latches the relay, feeds the blower motor, and the blower motor power transistor is what controls the speed of the blower motor. It is controlled resistance or engineered resistance that causes a voltage drop to make the blower move at different speeds. As we can see on the illustration, we have something called right there is called blower feedback. That's where the HVAC display is going to monitor that voltage drop or that control wherever the blower motor speed is. It wants to look at that. That is blower feedback. We're going to tie into that lead for our testing. The other lead is the blower power transistor base. That's the control. That's what the audio vac module is going to send out on an analog voltage to the base of this transistor right here. And we're going to scope that also. We're going to scope the actual ground of the blower transistor. The blower transistor, it's basically resistance. It does have resistance, much like the old school blower resistors back in the day, which were actual coils that we could see the different coils, and we'd see them get incandescent to see if they were working. This has that all internally. It is electronic. What you're seeing on the schematic is a simplified version of it. There's more to it than that. So I drew some resistances that no, it does have resistance. It does get hot, and believe it or not, this thing does have a bit of a high failure rate on Hondas. So anyway, we're gonna go through some situations. We're on 6 scope channels. Disregard channel G, that has been omitted. Channel A is the feed right at the blower motor. Channel B is the ground side of the actual blower motor, which will change with input to the audio HVAC display, because that's a controlled voltage drop. Channel C is an amp clamp at the blower motor. We will see that. We will look at rush-in current, and we'll look at when we see rush-in current, when we don't. As a general rule, the circuit is 40 amp protected. I was always under the impression that the rush-in spike will be about 75% of the fuse rating. So we're going to determine that as we run this circuit. Channel D, yellow, is we are monitoring the voltage, the feedback circuit, which basically will mirror the blower power transistor base circuit. You'll see that on the scope. Channel E is the channel E is the analog input to the base of that transistor. That's the actual circuit that determines the speed of the blower motor. That's feeding the base of that transistor in there. It's got a base emitter and a collector, and how much analog voltage goes into there determines the resistance that the blower transistor puts on the ground side of the blower motor. And this is actual ground. That's actual normal ground. That's the ground coming out of the blower transistor. We will see that as amperage goes up, obviously voltage drop goes up, and that is on the gray channel. It looks a little thick there. Anyway, that is channel F. That is gray. That is the voltage drop of the actual blower transistor. We are our ground lead is hooked to the battery negative terminal. This is an 8-channel scope. It does not have isolated grounds. It has each channel shares a common ground, so we're able to use one ground wire at the battery negative terminal. As you can see, that's the blower speed switch. That's what the driver, when the driver wants changes in blower speed, they turn that switch, clockwise or counterclockwise to determine how fast the blower runs. Anyway, let me get onto the scope, and then we're going to start the car and go through a situation where we're going to look at different resistances and different blower speeds. Let's get on there. Okay. All right, we got all our channels. We got 6 channels, and I'll explain each one of them. We will get the car running, and I'll just go through. I'll turn the blower on, and well, then we'll stop the scope and talk about it. So I'm cranking the car up. Okay. Let's start the scope. Okay. Okay. We have we're missing somebody. The red guy. The red guy should mirror the blue guy with actually the red guy is okay. This is when the blower motor is off. Right now we're going across the screen. The car is running. The blower motor is off. So we can look at our by the way, if you haven't taken a snapshot of the schematic, please do. Just roll it back to the time I was showing. I had the schematic up there. It'll make it easier to understand the scope captures. Channel red is on the ground side right at the blower motor, and basically that's going to mirror channel blue, which is at the feed side, because there is no ground. It's kind of deadheading through the motor, and the voltages are equal. And I'm going to get in, and I'm going to turn the blower motor. I'm going to turn the switch on the HVAC cluster. I'm going to turn it on. It's on full now. I went up, and we'll stop the scope and talk about it. Okay, I'm going to shut the car off. Okay, roll it back to the beginning. We got 14 screens here. Go to the beginning. Okay, this is when the blower motor was not on, when the car was running. Here we go. We got voltage. Okay, we got charging voltage at the blower motor on the blue channel. That's there. Let's look at the red channel and see what we got there. We have charging voltage there. Same thing. Okay, our yellow channel is our feedback, which is probably going to be about charging voltage, because you can look on your schematic, look at the feedback circuit. The HVAC module has to know what the voltage drop is across the power transistor. Our current is not flowing. We pretty much have an open circuit. We have no current. Purple is our controlled input to the blower power transistor, and it is very low. There is nothing going in. You'll see it start to go, and gray is our voltage drop across the ground of the power transistor, which is pretty much non-existent. I will go through the captures to see where I turned where the blower motor was turned on, and you'll start to see some action. Okay, there we go. There we go. Now we start to see some action. We got a little gap there, but that's life in the scope world. We got caught in the gap. We can basically see where I turned the blower motor on, that our red channel started to go low, because we started to put some resistance on the ground side of the actual blower motor. As you can see there, it's done in sort of steps. That's me turning the blower motor on. And we can see that we have actually less voltage drop, gets less and less. As the voltage drop is lessening, we can see our motor turning at a higher speed. Our current is going up. So there's definitely a parallel there between the voltage drop and the current. So if I take let me get the green channel is our current going to the blower motor. And as it steps, okay, we have 6 amps there. And our next step is we have 8 amps, then we have 10 amps. Then we look like we're at full amperage, about 13 and change. our voltage drop is actually increasing, which makes sense. Kind of Ohm's law here. We look at red, and we look at our voltage drop gets less and less as our current gets more and more. There's definitely a parallel there. Our yellow circuit, which monitors the speed of the blower motor or monitors the voltage drop for that HVAC module, pretty much mirrors red. So you can look on your schematic. That's kind of like it's just monitoring what the voltage drop is doing. And our purple guy is at a certain voltage that, let's see what that is. Okay, that's about 12 volts. Let's see, let's go back and, okay. Well, anyway, I'm going to do it again. I want to see a little more action on purple. I will start the scope. I will start the car. And, starting the blower motor on. Blower motor full. Blower motor off. Blower motor on. Blower motor off. Okay, let's analyze that. I just want to get a little more swing so you guys can see on purple that how that thing changes to affect the speed of the blow. Okay, here we have a better situation where our purple guy has more an obvious. Okay, there's a step. Okay, everything's starting to make sense here. Let's kind of zoom in on this puppy, and we'll kind of analyze it and talk about it. Our feed voltage is red. Is blue. That's the voltage going to the blower motor. As you look at your schematic, our red channel is on the ground side, right and coming on the ground of the blower motor, which is sort of an intentional drop that the power transistor does. You can see it kind of ramping down as I was turning that blower motor. I was creating more of more resistance each time I turn that. Actually, less resistance, okay, because the blower motor is spinning faster. So you can see the current going up here on green. The current is ramping up as the as the dial was changed, and we can see our control on purple. You see that steps? That's sort of stepped, and that's going up right here, and then that seems to be stepped. Let me make sure that is not duty cycled. No, that can't be duty cycled. That's just pretty much a stepped voltage that affects the speed of the blower motor. And we can see the red has more voltage, has less voltage drop as the blower speed increases. And of course, look on our gray channel. That's the voltage drop of the power transistor. And we can look at it from, I'm going to do some stretch because I'm on a 20 volt scale. We're going to look at voltage drop. I want to stretch the gray guy to see that current flow has an effect on voltage drop. So let's do this. And we'll see that. Okay, I stretched the gray guy. Obviously, that's our voltage drop. Wow. Okay, that definitely was what we expect with more current flowing. We've got about 48.86 millivolts. And then down with no current flowing, we're down to pretty much nothing. But that's the definite effect. You can see the effect that's normal. That's the voltage drop of the power transistor. So anyway, we'll get back to here, and I will start up again. One thing I want you to, that I in researching this thing, I noticed I wasn't really impressed with the Russian current. And I thought about it, and I said, I know that the Russian current is actually less than the normal running current. That really shouldn't be. That's not the way electric motors really work. And I looked at the circuit, and then I thought about doing something different to sort of determine Russian current. Russian current's real important because that tells us the condition of a motor. Sometimes when that's excessive, a motor could be wearing out. It could have tight bearings, tight brushes, things like that. So that's something we definitely, any motor, like a fuel pump or something, we want to look at. And I really wasn't impressed with that point there right here. And I thought about, for some reason the circuit is, I can't really explain why not, but nonetheless I'm going to do something and show you something. We're going to pull the blower relay out, in and out, and see a different, we're going to see a different rush in current. Anyway, let me start the car. I'm going to turn the blower motors on full. Okay. Oh, I got my gray guy. Yeah. So when you stretch, you got to put it back. The gray guy's hogging the screen. Let me put that puppy back down to. Yeah, I had her. I put them on 1. That's my kind of default number on the Pico. I think it works. Anyway, oh, no, I overshot. Anyway, okay, you can see the current. Let's kind of take a look at a normal running current going across the screen. I'm going to do something. Okay, how many amps? At high speed, we're flowing about 14 amps, okay? The circuit, it's got a 40 amp fuse protecting it. So that looks pretty good. One thing I want to say, let's take a look at the commutator bars. See, this thing has got 250,000 miles on it, and they're kind of nasty. I've got to see a good one. I've seen better Hondas. Anyway, we can see something. That's our commutator bars. That's our, we got a lot of, that's a worn, that motor's probably seen better days. There's a lot of, right here's maybe could be a little dead spot, but it's pulling it. The inertia will pull it through, but nonetheless, there's something to keep an eye on when you're testing the condition of a blower motor. Also bear in mind that motors can take out power transistors. They can have a collateral effect on them. So if you diagnose your customer's blower motor as bad, think about what also is in that circuit. And you may want to price that out on your estimate, or give the customer a heads up about something like that. So anyway, same with fuel pump driver modules and fuel pumps on Fords, things like that. Think about the collateral effect, because if a motor's drawing excessive current, that component's also getting excessive current. Anyway, I'll start the scope and take a look at the current going across the screen. We're running about 13 amps, and I'm going to remove and put back the blower relay so we can shut the current off completely to look at something. I want to lower the scale so we have some room to look at what we're about to look at. So let's go down here. Okay, just watch the green and okay, you probably saw something. And what I did was I removed the blower relay just for a second and put it back. Okay, now we got something. That's a spike. That's what I want to take a look at. That's what we want to give some look at, because that tells us something about the amount. How much is that rush in current? That's the current to get the motor moving from a sedentary state. That's 37.32 amps. Okay. Remember I told you that the rush in current is usually 70% of the rating. So we take 37 over 40. Okay, maybe not quite, but nonetheless, it didn't exceed the rating of the fuse. Just something to bear in mind when we're checking motors. That I say is a little high. As I said, the motor's original. It's quite old, but nonetheless, we were able to see the rush in current. So basically, I had to just shut the circuit down and reapply the circuit to get that. I couldn't get the rush in current just by the blower switch on the instrument panel. So anyway, we'll just take a look at one more scenario. I'm going to kind of go through a slow I'm just going to move the dial in slow increments up and down so we can just see one more time what it looks like. Okay, I did that slow. We can see the step relationship of everything. And we're almost ready to end this video. And we'll stop it, roll it back. You can see right there, you see where we're changing. You see our purple's changing, our current's changing, our yellow's changing, and our red is changing. Our blue guy is kind of missing in action. We got to get that guy back. Okay, blue is the feed. That doesn't change that much. But nonetheless, you can see the stepping action. Current goes up. As current goes up, our red goes down because we're getting less voltage drop. The slower the blower motor spins, the more voltage drop that would be on red. So as you look at your schematic, you can see how the blower power transistor is a controlled voltage drop that affects the speed of the blower motor. Anyway, I hope you enjoyed this video. Just bear in mind about cause and effect when excessive current's flowing. Look at that whole circuit and see what else you may want to recommend when you diagnose like any motor, cooling fan motor, blower motor, fuel pump, and think about the relays and the components in that circuit. Thank you very much for watching. Have a great day.